Where we were looking at is in Chapter 3, X-ray production, and we had looked extensively at using tungsten targets, and we came across two mechanisms of X-ray production, the Bremsstrahlung mechanism that involved the incident electrons with high kinetic energy suddenly slowing down, and whatever energy they lose is converted to X-ray energy and heat energy. But then we also saw that the second mechanism was characteristic radiation production. That mechanism involved the incident high-energy electrons interacting with orbital electrons and yielding monochromatic energies. And so let's pick up at that point. We considered the possibility of other types of target materials with our experience in mammography. In mammography, we saw that you have very little contrast between tissues. They don't distinguish themselves very well because they are so similar. They absorb radiation in such similar manner that one tissue is very poorly contrasted or distinguished against another tissue. So we were on a quest. In the special case of mammography, how to increase the subject contrast. And the way we increase the subject contrast is by lowering the energy. And we made an analysis and we came up with the magic number of 20 keV. 20 keV is the optimal energy to visualize and to image a typical breast, typical being defined as typical thickness, typical density, typical composition. 50-50 composition is considered typical, 50% soft tissue, 50% fatty tissue. So now the question is, how do we get 20 keV? And we had already seen that in the Bremsstrahlung spectrum, the maximum energy is equal to the voltage that you impress across the tube. So to get 60 keV Emax, you need 60 kVp voltage across the tube. And we saw that incident on the patient, 1/3 of the maximum is would be the average energy. So if we take a typical Bremsstrahlung spectrum at generated at 60,000 volts peak, you will have an average of 20. And you would think at that point, I've accomplished the mission. I've got an average of 20, which is the optimal energy. No, you don't, because along with the 20 comes all these low energies that just give you dose. And along with the average of 20, you get all these higher energies above 20, and they are photons that just reduce the contrast. You'll be having photons arriving at the image plate that don't deliver very much information in terms of contrast. So the overall image will be poor. So this is not the way to get an average of 20. Now, what would be ideal if we could only get a distribution that looks like this? Only one energy, purely at 20 keV. Nothing below that just produces dose. Nothing above that just produces loss of image quality, the reduction of subject contrast. Well, we don't have such beams that just yield monochromatic energies, but that is monochromatic energies reminds you of characteristic production, where you do have monochromatic energy. So now the strategy is, well, let's see if we can find a material that at least concentrates at more 20 keVs. How do you get a material that has characteristic radiation at 20 keV? Well, remember our discussion? If you want 20 keV characteristic radiation, then you got to get a material whose binding energy is 20. Why? Because then electrons from infinity that fall all the way down to the K-shell, and if that K-shell has a binding energy of 20, out comes a monochromatic beam of 20 keV. And we find that the material that has that binding energy close to 20 is molybdenum. And molybdenum actually has a signature. The characteristic radiation energies are a characteristic and specific for a material. Molybdenum has 19.5 and 17.5 as a signature. Well, not quite 20, but close enough. We're going to zero in on molybdenum as a target material. Why? So that we can get a greater yield of 20 keV photons, the optimal energy photons. But now we find an additional feature with the molybdenum. Not only will it give us monochromatic 20s, but because molybdenum is a low Z material, meaning it has very few protons in the nucleus. Remember that the proton number defines the atomic number. They're equal. Well, if you have fewer protons in the nucleus, there'll be a lower attractive force exerted on the incident electrons, and that was the mechanism of Bremsstrahlung. So, in that result, fewer Bremsstrahlung events. So now it turns out that monochromatic radiation will dominate with the monochromatic, with the molybdenum. Here, you remember in our discussion of tungsten, we saw that Bremsstrahlung dominates by far, and that characteristic was as low as 10% of the total. Very little characteristic radiation compared to the Bremsstrahlung, but with molybdenum, everything is reversed. Now, the dominant source of radiation is the characteristic radiation production mechanism, and the Bremsstrahlung is of a lesser a contributor. And again, why a lesser contributor? Because it has a lower atomic number, and there's lower attractive forces on the electrons, and they no longer become the dominant interaction. The Brems is no longer the dominant interaction. Notice that the same conclusion is also for the rhodium type targets. We'll be talking about rhodium presently. Okay, so I think this is where we left off last time, looking at this particular slide, where now we have I've drawn in a typical molybdenum target spectra that has a underlying Bremsstrahlung, but a more dominant characteristic peak, and I'll just call it 20 keV. And you would think at that point that a mission is accomplished. No, because we're going to tweak this another step. And because notice that there's still high energies present. And what do high energies do? They lower the image quality contrast. Notice that there's also low energies present. What do? They increase the dose. Low energy photons are easily absorbed. So enter another concept. Let's put a filter in place that preferentially absorbs the lows and the highs, but get this, but allows the characteristic radiation to go through 100%. No attenuation of the desirable 20 keV photon. How will that work? First, I'll show you the mechanism, and then I'll give you the principle behind it. Notice if you have a filter, the filter will knock out some of the high energy photons. Hey, that means then that you're going to have better subject contrast. See, if you reduce the high energy photons, those photons above the 20, then you get better contrast. If you reduce the low energy photons, well, then you're going to get better dose, lower dose, because you're going to pre-filter them before they even get to the patient. But what is this about allowing the monochromatic energy to go in totally unattenuated? This is almost like magic. There's a choice of filters that, and specifically if you match the filter with the target, so that if we have a molybdenum combination, molybdenum target, molybdenum filter, this is magic, because adding the same material as the target material, a Mali combination, the theorem and the principle is any material is invisible to its own characteristic radiation. In other words, characteristic radiation from molybdenum will go right through a molybdenum filter as if that filter was not there. And there is no attenuation of that valuable 20 keV characteristic radiation. How is that possible? Well, we're going to be talking about that in chapter 5. Okay, but right now I just give it to you as a principle, and that applies whether you're talking any combination of target and filter material. Later on, we're going to talk about rhodium-rhodium combinations. Okay? And specifically, what if we don't have atypical breasts? We had calculated that the optimal energy for a typical breast was 20 kV. But what if it's a thicker breast? What if it has greater density? Well, if it's thicker and or denser, that means that the photons will be more readily absorbed in transit through the breast. So that we have to have a slightly higher energy to be able to penetrate the thicker and or denser breast. Well, how much higher? Here we go again. We go through an optimization procedure and we come up with the new condition that it is denser and or thicker. The energy optimal is 23 kV. So now back to the periodic table. What material will have a binding energy of the K-shell at 23 kV? It's the same approach we did for the molybdenum. In this case, however, we find rhodium. Rhodium has exactly 23 kV. Rhodium is also a metal, so that you can fashion a target out of it. And just for the same reasoning that we use a molybdenum filter matched up with a molybdenum target, we'll use a rhodium filter matched up with a rhodium target, so that now we have two possibilities. We could have a moly-moly combination if the breast is typical, or we can have a rhodium-rhodium combination if the breast is thicker and or denser. And it turns out that we have a third possibility where you'll have a molybdenum target with a rhodium filter. We cannot use a rhodium target with a molybdenum filter because you'd wipe the beam out entirely. But those are the three possibilities. Now, the machines that have that facility, not all MAMO machines have that facility of providing both molybdenum and rhodium. There's only a few vendors that have that combination available. And but the way those would work would be the following. You have a filter wheel. One half of the filter is molybdenum, one half of the filter is rhodium. Okay? You have a target that has two targets for each size. You have a large and small molybdenum target, and you have a large and small rhodium target. You got to have a target material that combines or that has separate tracks, one for molybdenum or one from rhodium. And the way it actually works is as follows. The tech sets up the patient, presses the button, and the machine puts out a very short pulse of X-rays. It's a test pulse of X-rays going through the breast. And for instance, if the intensity detected behind the breast is very, very low, what does that mean? If you have a very low intensity getting through the breast, what it means is that the breast must have been very thick. It must have been very dense. Well, then that sends a signal to the filament, to the electron focusing cups, and you focus the electrons onto the rhodium target because the system had detected that the breast was very thick or very dense, or both. So that now the electrons are falling or accelerated upon the rhodium target. Likewise, the electrons are focused on the rhodium target, and the filter wheel rotates, and now you got the rhodium target come to bear. Okay? If the original little short X-ray pulse had indicated a relatively large intensity getting through the breast, that would imply that the breast is relatively thin. It's more typical, both in thickness and in density. Then a signal goes to the focusing mechanism of the electrons, and the electrons are focused on the molybdenum target. And at the same time, the filter wheel turns around to bring to bear the molybdenum filter. And then you can also get that third combination where you get a molybdenum target with a rhodium filter, all based on that little test shot. Once everything is set, target and filter, then the main pulse of X-rays is shot through the breast and you get your image. Okay, that's the way it works. And which now brings up a question. We've just seen that we use molybdenum and or rhodium for these mammography systems, but why don't we use the tungsten targets that we had originally discussed? It's used for radiography, fluoroscopy, and CT. How come we don't use specialty targets and matching the filter with the specialty target? Well, the target we do use for these modalities is tungsten, but we don't match it with a tungsten filter because we don't have the unique situation, the specialized situation that we have in mammography. We have to image the whole spectrum of thicknesses, and they can be pretty thick. The whole spectrum of densities, and different parts of the body could be very non-dense, and other parts could be very dense. So the radiography, fluoroscopy, and CT have to be prepared to take on thin patients, thick patients, a range of densities, the range of different tissue types, atomic numbers. What we do is we just use a universal filter, which is aluminum. Okay, and in fact, this is so universal that even when you use molybdenum or rhodium, you specify its filtration in terms of aluminum equivalent. There's a new term for you, aluminum equivalent. Whenever we talk about filtration, we always refer to aluminum equivalent. It may not be aluminum, but we're going to specify its thickness in terms of how equivalent to molybdenum it is. Now, here is a trend that we have with digital mammography, and that trend is back to tungsten targets. Why would we want, after all this discussion, why would we want to go back to tungsten targets? We saw that molybdenum and the rhodium were optimum, but now why back to tungsten? Here's a couple of reasons. Number one, you have much more output. There's a lot more radiation generated. Remember that you really took a hit on bremsstrahlung production when you went to these low atomic number materials? Well, we should go back to a high atomic number tungsten. Now you're going to get a lot more output. A lot more output means shorter exposure times, reduction of motion problems. Okay, and along with those tungsten targets, there's a trend to go back to a higher kV. And again, the higher kV not only gives you the more outputs, but you get more penetration. And more penetration means that you deliver more radiation to the image plate, less gets absorbed in the patient, less patient dose. But what about the contrast? The whole reason we left the tungsten and went to molybdenum and rhodium was to enhance contrast. Well, you can only play this game with digital mammography, going to slightly higher KVs with tungsten targets. In digital mammography, remember you have a computer backing you up. And on the computer, you can, with various algorithms, recapture some of that contrast. You can adjust the contrast with your computer. Okay. Just like when you take your a digital camera and you take an image and you want to play around with the contrast, you know that you can, there's mechanisms for enhancing the contrast of a digital image. Well, that's available to us via the computer. So this is a trend that not all vendors are going to it at this point in time, but that seems to be a trend that I suspect that will go. The advantage of output and penetration is so enticing that that there is this approach, a little bit higher KVs with tungsten targets, and they find that a silver filter is a more efficient filter. Okay. And as we said at the bottom of this slide, you recover some of that subject contrast via the computer. Okay. Okay, enough said for different target materials. Are there any questions on that? I want to redirect our attention. So if there's any questions, just pipe them in. Have you ever seen a technologist in the back manipulating and fiddling around with these dials and these buttons and whatnot back at the console. What is he doing back there? Now, up till this point, you really don't give a hoot what he's doing, right? You just want to press the pedal and see the image you want to see, and you know, do the have a successful examination. Well, from this point on, I want you to be more sensitive to what the tech is doing there. What the tech is doing in the back at the console determines what you get to see. Okay? Now, because of his art, because of his experience and knowledge, he can set up the machine so that you see what you want to see. But you should be able to identify the parameters that are being manipulated and how they affect your final image and how they affect patient dose and how they affect your dose. One of the little rules that we have in fluoroscopy is your dose goes as patient dose. If you double the dose to the patient, yep, you double the dose to you. Okay, so keep that in the back of your mind. Well, these are the technique factors that we're going to be talking about, at least initially. These are the things that have to be set for you to finally get an acceptable image. I'm going to go one by one down the line. Let's talk about exposure time first. What is exposure time? Here we go back to our X-ray tube. Remember this story? Electrons via thermionic emission coming out of the filament, accumulating in the electron cloud, and when you put the voltage across the tube, plus negative voltage here, electrons will be accelerated and out comes the X-rays. The exposure time is just the time duration of the exposure. It's the time that you allow the electrons to continually flow across the tube. Okay, but the more important parameter here is it's really exposure time is really, and this is the last item on the slide here, the exposure time is really a measure of how many electrons finally get to the target. Does that make sense? The longer you allow these electrons to flow, the more electrons you deliver to the target. The number of electrons delivered to the target is going to be the key parameter. Okay, and what happens when you do change the exposure time? Well, for instance, here I've illustrated that. I've made a plot of how many X-ray photons are being produced and as a function of how much energy do they have. It's like a frequency distribution. How many photons do you have of any particular energy? And the yellow curve is an exposure totally 1 second. You've delivered a certain amount of electrons and you get a certain number of X-ray photons finally produced. But what if you double the time? Double the time to 2 seconds, now you have the red curve. And but look at the general characteristics over here. Number one, notice that you get more output, right? And that more output is directly proportional. It turns out, and it should take this home with you, if you double the time, you double the amount of radiation that you've produced. You double the number of photons incident on the patient. Okay, that's observation number one, more output. Observation number two, there's no change in the energy distribution. You had a certain Emax. Remember, the Emax is determined by whatever voltage you put in. When you change the time, that's not a change in voltage. So Emax point is fixed. Go back to that. And remember, we saw that you have a certain effective or average energy. The effective energy incident on a patient is 1/3 of Emax. But notice that the E effective hasn't changed. No energy distribution differences. You just get more photons at every energy. And specifically, you get, if you double the time, you get twice the number of photons at every point. So let's start making a list of features over here. As exposure time goes up, we say that the beam quantity goes up, the total amount of radiation goes up, and it's directly proportional. I'll be using the abbreviation DP for direct proportionality. And what does that mean? If you double one, you double the other. If you half the one, you half the other. Whatever you do to the one parameter, in this case, I'm talking about time, you've doubled the other parameter, in this case, the beam quantity. Double the time, double beam quantity. And there's various synonyms that we can use. We can talk about the output of the unit. We can talk about the intensity of X-rays. We can talk about number of photons. We can talk about milliröntgens coming out of the tube. We can use the word exposure. Air Kerma, remember air Kerma? To refresh your memory, stands for kinetic energy released in materials. It's energy per unit mass available as a result of the radiation. So those are measures of beam quantity. What else can we say? Well, if you've increased the beam quantity, what happened to patient dose? The patient dose is going to go up, and notice that, directly proportional. So if you double the exposure time, you double the patient dose. Okay? What happens to what you get to see in the image? Well, I'm going to consistently talk about two different modalities. The more important modality for us is obviously the digital modalities, but on your ABR syllabus, they do ask some questions on films now. Films are very quickly going out the window, and I'll be emphasizing the digital effects. But let's talk about the film effects first. If you give more radiation to a film, the film gets blacker. We say that the film density increases. Okay, not quite directly proportional. So notice I don't have a DP there. It's not directly proportional, but they track in the same direction. As the exposure time goes up, the amount of quantity of radiation goes up, the blackness on the film goes up. But the more important one for us, the digital effect. I have to introduce a new concept. So far, I've introduced the concept, two other concepts. I mentioned contrast. Remember contrast? It's the ability of tissues to distinguish themselves in the background of other tissues. I've mentioned resolution, your ability to see fine detail. Now I'm going to round that out with the third image quality parameter, noise. Noise. There are three major factors that determine how good an image you get to see: the contrast, the resolution, and now the noise. What is noise? I'll give you a definition. In a subsequent chapter, we're going to really jump into noise. But noise, in terms of a definition, is just the statistical variation of intensity at every image point. The statistical random variation of intensity, image intensity, at every point in the image. Okay, and we're going to have to talk more about that. There's more to it than just that, but I'll give you the principle, and that is that when you have more radiation, which you do if you increase the exposure time, when you have more radiation, that reduces the noise. That reduces the noise. So we have, as your exposure time goes up, noise goes down, which implies that you get a better looking image. Noise degrades the image. Now, here is what has been experienced when we first went to digital. It's pretty much under control these days, but when we first went to digital, what was observed was what we call dose creep. Dose creep. I understand that that term was used two board questions 2 years ago on the boards, and dose creep. This is what that's all about. Since if you give a little bit more radiation, the image looks better, well, that's positive reinforcement. A tech that gave a little bit more radiation looks at the image and says, hey, this is better than what I was doing before. So now he adopts his techniques to include a little bit more exposure time because the images come better. You always want to get a better image. But remember, by increasing the exposure time, you also increase the dose. So, and as time goes on, the techs would again, for one reason or other, if they have a higher exposure, hey, this looks even better. From now on, we'll give it a little bit more exposure time. That's dose creep. And that was found in a good, where it was studied, it was found almost invariably from institute to institute. People were giving a little bit more dose every year. the dose was creeping up. And because more dose means less noise means better looking images. So dose creep. There is going to be a limit to how much time you give. Remember, the exposure time you give also affects motion. Here's another a name for noise that you may have heard, a very popular name. It's also called quantum model, which makes it even more esoteric. I'll be using either a quantum model or QM, its abbreviation, or just plain old noise. To give you an example of what we mean by noise, take a look at this. Tell me what it is. Can you discern any shape in there? Can you see an image in there? I can't see an image. It looks more like some Milky Way or some, astronomical image of clusters of galaxies or what, a bunch of stars, right? You really can't tell what it is. There isn't very much image points. There's not very much information there because there wasn't enough photons filling in the image. Let's fill in the image some more. Let's add more exposure. Let's have more radiation to this image. Now can you see something? The difference between these two images is that the one on the right has more photons filling in the image. There is less statistical variations between one point and the other point. Over here you had black and then a big jump and then finally all white and then another big jump black. It's a salt and pepper looking image. Here you still have a noisy image, but now maybe you can start seeing that it's a girl looking up, or at least the image of a face looking up to the upper right-hand corner. Okay? Your ability to see images depends on how many image points have been filled in, how much radiation, how many photons are contributing to the image at every image point. Here's the complete sequence of images. I gave you these A and B, the first two in that prior slide, and then I'm going up further with more photons, and then in the lower left, I pick it up with more photons, more photons, more photons, and you can see that you get progressively a prettier and prettier picture. Now, these were done with light quanta, light photons, but they illustrate what we're getting to. As you add more and more, in our case, X-ray photons to an image, the image gets better and better because you have less and less noise. The challenge to a radiologist is, where do I draw the line? Could I have successfully completed my examination with the lower left-hand quantity of dose to the individual? Do I really need a prettier and prettier image if I've already made my conclusions and seen what I want to see at a lower radiation exposure to the patient, which really means a lower radiation exposure to yourself? Okay? That's the challenge. Where do we draw the line? But in general, the principle is that the more photons you use, the less the noise, the less the quantum model. Okay? But that's a good. But the downside is, if you give more photons to get more photons at the image, that means you have to have more photons incident on the patient, which means more dose to the patient. Okay? Here's an actual CT image illustrating the noise. On the left, we have a relatively noisy image. On the right, we have a more smoother image, a less noisy image, and you can appreciate borders, contours, features so much better with the image that has a lower level of noise, a lower quantum model. But how did you get to the image on the right? You had to give the patient more dose. And in CT, you may not be at risk of exposing yourself. That is typically more in fluoroscopy. But we still have to deal with the dose to the patient. We still have to deal with the idea that if you want to give more dose, if you want to give more photons, you usually do it with adding time. But then adding time gives you the motion problem. Okay. Well, let's continue our list of features. I've just discussed the image effect, noise. Let's move on, and we'll be talking much more about noise later on. Let's go to another feature which we call the beam quality. I'm not referring to image quality. Beam quality is referring to the relative penetration of the beam. How well does the beam penetrate the patient? Well, the penetration of a beam depends on the energy of the photons. So this is going to depend on the effective energy, the Emax, the energy distribution. Okay, uh, 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 is there any change in the energy distribution when you increase exposure time? No, there is no change in Emax. There's no change in E effective. So notice I give a parallel arrow, meaning no change. No change in penetration. Another word for penetration is transmission. Another term that we use to indicate the concept of penetration, the ability of the photons to get through the patient or through any type of material. Sometimes we talk about the half value layer, HVL. Half value layer is defined as that thickness of material that will reduce the intensity of X-rays down to 50% of its original value. Half value layer, very common measure of penetration. And it's something that you can visualize. If you take a filter in your hand and you stick it inside of an X-ray beam, question, how much does that filter reduce the intensity of X-rays? The thicker that filter, the less penetration you have, the less transmission you have, more of it will be absorbed within the filter. Well, how thick must that filter be to reduce the beam down to 50% of its original value? That's the HVL. A cousin, a related measure is a TVL, 10th value layer, the thickness of material required to reduce the intensity of a beam down to 50%, I'm sorry, 10% of its original value, 1/10 of the original value. Another term that we use to describe penetration is how hard is the beam. We talk about hardness. There are hard beams and there are soft beams. A hard beam is a beam that's hard to filter out. Why is it hard to filter out? Well, it must have very high energies. The higher the energies, the harder it is to filter that beam, to remove and to lower the intensity. So we talk about the hardness of a beam. A soft beam would be a very low energy beam. A low energy beam is very easily absorbed out and has very little penetration. So those are common terminology. How hard the beam is, how soft the beam is. The mammography uses very soft beams. CT scanning is over at the other end. They use relatively hard beams. In fact, maybe you've heard the term beam hardness in your travels around a CT scanner. The beam hardness artifact, which we'll talk about at some other point. Then the final at this point we want to make concerning subject contrast. Subject contrast, remember, goes as energy. Later on, I'm going to modify that statement, but at this point, I've just defined, remember this, as energy goes down, subject contrast goes up. Energy goes, subject contrast goes inverse with energy. As one goes up, the other one goes down. But we've just seen that the beam energy is unchanged. The beam quality is unchanged. Well, if the beam quality is unchanged, subject contrast is unchanged. Very popular question on the boards. And the question may, or the illustration may go as follows. A technologist observes a relatively poor contrast in an image. What should he do? And then they'll give you things like increase the exposure time. Well, we just saw it. Increasing exposure time doesn't necessarily increase the subject contrast. Okay? I'm going to modify that statement later on, but for now, you have to change an energy if you have low contrast. If you have low contrast, you go to a lower energy. That would be the answer to that question. Okay? There is, I've mentioned this, that if you have an increased exposure time, well, then you're going to have motion problems. Okay, so you have motion problems and the possibility of motion streaks in digital imaging. Well, okay, just how to make calculations. I'm going to put the equations up, but they're really very simple calculations that you can do without equations. For instance, if you have if you get an output, if you have an intensity of radiation 5 milligrays at some distance, and you got that by having a half a second exposure, how much would you have if you have a 1 second exposure? See, you don't need math for that. You can see right off that 0.5 to 1, you've doubled the time. Double the time, you'll double the output. Well, if you had initially 5, well, doubling the output will give you 10. The actual mathematical procedure looks like what we have up here. Where the final output, that's a subscript F, this final output is what you started out with the ratio of times. We just saw that the ratio of times here, 1 over 0.5, is a factor of 2. So you multiply the output initial by 2, you get your final answer. Okay, I put these equations up there for those that may want to be more quantitative. On the boards, don't use an equation, use your head. Double the time, double the output, double the dose. Okay. Before we leave exposure time, I'm going to say a little bit more about the exposure time. There's a list of things here that you should take home with you. I'm introducing another term for you now, the temporal resolution. How good are you able to see details if the detail is moving in time, okay? Which would happen, for instance, as you increase exposure. Motion blur, motion streaks. If you were trying to get a 3-phase liver scan and you have long exposure times, forget it. You're not going to be able to do it. You have to have relatively short time so you can catch the various phases. Your ability to do breath hold scans and have the whole scan sequence within one breath hold to help you with your distinguishability of tissues, your resolution, etc., your image quality. And of course, whenever you have trying to image a moving organ, like cardiac imaging, well then exposure times are going to be critical. Okay, just to give you a picture of what we mean by motion blur, you can, on the left, you can see these artifacts produced by motion at the relatively long scan time, and you can see that those would be motion artifact free with time. In CT scanning, you get more artifacts as compared to getting more blur. We've been talking about time. I want to introduce the idea of a photo timer. A photo timer, sometimes also called AET or AEC, automatic exposure termination time, or automatic exposure control C. And a photo timer is a device that will allow the machine to make its own decision as to when to stop the exposure time. Okay, modern machines, when we use the so-called photo timers, remove one decision level from the tech. The tech doesn't have to set the time. The machine turns itself off at the correct time. How does it know how to turn itself off? It has a series of 3 chambers shown over here. This is a picture, actual picture of next time you're in a radiographic room, look at the upright chest stand, and I suspect that you'll see these 3 figures. Sometimes they come as squares, sometimes they come as circles. Doesn't matter the geometry. The point is that there are 3 sensitive detecting devices, X-ray detecting devices. So, for instance, you would place the patient up against the chessboard, and you would place the lung field of the patient to coincide with the approximate positions of the 2 lateral chambers. And then these chambers have been calibrated by the engineers, so they will turn off after a specified amount of radiation that reaches the image plate. And the specified number of amount of radiation specifies the acceptable noise in the image. Remember the relationship between noise and exposure. So these little chambers will detect the radiation and turn the material off at the appropriate time. So if you want a PHS, you set the patient up and you choose those two lateral ion chambers. If you want a lateral upright chest, then you would typically choose the chamber in the front for the lung and a chamber in the middle for the spine, heart shadow, and the tech in his training knows what combination of the three to set for every examination. Okay? We call these ion chambers, but in any case, we always set this up. We always set this up so that we always get the required noise, and if we in the old film world, we always get the same film density. Okay? And whatever combination of ion chambers you use, those are the ones that will yield the anatomy behind those particular chambers or in front of those particular chambers are the ones that will determine the correct noise level or the correct film density on the image. I want to make this point before we move on. Also, you always place these ion chambers between the patient and the image plate. And I've already mentioned these for the PHS film, but let's say a little bit about the ion chambers. The ion chambers are going to be very, very important for us. We use it in radiology, we use it in nuclear medicine, in a lot of our instrumentation, and it's the favorite means by which we can measure radiation. There are other means of measuring radiation, but this is one of the favorites. It's one of my favorites. An ion chamber looks like this. You have a plate with positive charge, you have a plate with negative charge, and you have a gas enclosed within those plates. Typically, that gas could be in a typical ion chamber, they're air as a gas, and they're air in the phototimer cells. X-rays come in. What do X-rays do? They produce ionization, and ionization produces ion pairs, right? You liberate electrons. What happens to the electron that you liberate? It goes off toward the positive plate. What happens to the residual atom that is missing the electron, that you had the electron removed from? That goes and migrates to the negative. And when they get to their respective poles, they neutralize the charges at those poles. Well, do you see that if you knew how much charge you had before you radiated, and then you measure how much charge you have after you radiate, every charge you lose is one ionization. You've just measured every ionization event that occurred in the gas. Every ionization event results in the neutralization of a charge pair on these pair of poles. We are on our way to determining exposure, the milliroentgens, the air kerma, based on the proper calibration of these of chambers. Okay? Okay, enough said for exposure time. Let's go on to the second parameter, and that is the milliamperage. What do we mean by milliamperage? Back to the X-ray tube. And again, we see the electron accelerated between the filament and the target. The tube current. Remember, what do we mean by current? Current is always flow of electrons across the tube per unit time. Flow is always, current is always the flow of electrons per unit time. And this is what we have, and we call it a tube current. It's flowing across the tube. And the unit of this of current is the ampere, abbreviated amp, and the important idea for us is that the milliamperage determines how many electrons arrive at the target. Remember, that's exactly what we said for the exposure time. Exposure time determines how many electrons arrive at the target. So does the milliamperage determine how many electrons arrive at the target. So now let's take a look and compare the resulting spectrums. Here we have 100 MA in yellow. There's 200 MA in red. Notice that we have the same observations, that you have a directly proportional variation of number of photons. You double the MA like I've done here. You've doubled the output. You double the number of photons being X-ray intensities being produced. And again, there's no change in distribution. And as a result, everything we said about time is also true for the MA. So there's nothing new there. As MA goes up, your beam quantity goes up, directly proportional. But if you have a increase in beam quantity, you're going to have an increase in patient dose, directly proportional. More MA means more radiation, means less noise, more blackness on the film, no change in beam quality because there's no change in energy. And if there's no change in energy, there's no change in subject contrast. And of course, a changing MA is the preferred way of getting more radiation because it doesn't impact the motion problem, right? You're just getting more electrons per unit time. You're not extending the photon arrival at the target in time. You're just getting more electrons arriving at the target. So they may ask you a question. You have a noisy image, not noisy image. You have a motion problem in an image. How will you minimize the motion problem? Don't choose increasing the time. You would decrease the time to get less motion. If they tell you, well, you got a noise problem in the image, and the noise problem means that you have to increase the number of photons, don't increase the number of photons by increasing the time. Do it by increasing the milliamperage, because that doesn't affect the motion. Okay? And again, because of direct proportionalities, you can do this in your head. If you had an initial output of 5 milligrays at 50 MA, but now you go to 100, 50 to 100, you've just doubled the MA, then you will double the output. So instead of 5, it's 2 times 5 or 10 milligrays, just like we did before. But those that like the equation, there's the equation, and I needn't discuss it any further. This K over here is referring to the fact that tubes do change output, and but this relationship still is the same. So from tube to pool, one tube versus another tube, don't expect to have the exact same initial output from one room to another room. So there is a little variation from tube to tube, but it's constant for any one machine. Okay, gee, our time is almost up, but I'm going to think I'm going to simplify this a little bit and delete that statement. Okay, moving on. Let's go on to another technique factor. I think I can just barely squeeze this in. The milliamperage second product, the product of the time in seconds and the MA. And so, for instance, if you had 100 MA and a tenth of a second exposure, the product would be the product of those two numbers. It would be 10 MAS. And when we talk to the technologists, you're going to find that many times they talk MAS. They don't tell you. If you ask them what technique that you use on Mrs. Jones this morning, they'll say something, well, I use 100 at 10 mass. That would be, the 100 would be the 100 kVp, 10 mass would be the MAS product. But it's the same effect as MA or time. How do you double the MAS? By doubling either the MA or the time. So it's back to where we were before. Here is a comparison of 100 MAS and 200 MAS. No change in energy and the directly proportional change in output. So everything we said about time, everything we said about the MA is also applicable to MAS. So that makes it really simple. Okay. And it's a good point to, well, the equations that we saw before, if you double the MAS, you start out with 5. If you double the MAS from 50 to 100 MAS, you just double the value, the initial output, and you get 10 milligrays. Well, this may be a good time to stop. Are there any questions before we let you off for the day? Well, you all have a good day now.
Thanks, Dr. O'Connor.
Sure thing. Have a good one.
By the way,